Okay, so we're moving right along in the infrared world. See, if you just keep it related to real life, then these molecules are not bad to deal with. You're just going to have to realize how they like to work out. And that's the purpose of infrared. So we're going to have to figure out what gym buddies do what. Some days they like arm day, some days they like leg day, but you never really know until you find out their routine. And that's what we're getting ready to figure out and discover. What are these molecules' routine? What do they like to do when they go to the gym and work out? Because some will do one workout, but they won't do any others, and that makes them different. So, just a recap of what we said before. In the instrument, what's going to happen is that we're going to place a sample in the machine. And this sample is going to be bombarded with a wavelength of light. And this wavelength of light is going to be in the infrared range that we talked about up here at the top. This sample will then absorb light, just like the samples absorbed light in the UV vis instrument. They will absorb light in the infrared as well. And when they absorb a certain amount of light, when the machine begins to scan and it looks at this window of nanometer, when the molecule absorbs light, it's very particular. And certain wavelengths will allow it to stretch, and certain wavelengths will allow it to bend. And all molecules will do the workout differently. And that's how we are able to pick up on the types of molecules that are being analyzed in the infrared world. All right, so only when the energy matches the bonds, only when the gym offers the workout routine that they're interested in, will they go to the gym and work out. Okay, same thing happens in infrared. Only when the light beam offers the light that the molecule wants, it will then do the workout and stretch and bend for us so we know what type of molecule that it is. All right. So one of the things that I need to kind of talk about with infrared before we go any further is what is its purpose, right? Infrared does not give us any quantitative data. You're probably gathering that now. Stretching and bending, give me a break. That's not going to give me any quantitative data. No numbers can be associated with infrared for the most part. There are some exceptions. What infrared is really good with is qualitative. Qualitative means what do I see? What do I observe? And the qualitative in this case are going to be the functional groups. All right, so what do I mean about functional groups? Well, let's say that the molecule has an OH group, an alcohol. Well, that alcohol will bend and stretch in a certain way, only the way alcohols like to bend and stretch. So if I see bending and stretching that goes on at a certain location, then I know that an alcohol is present to the gym for that day. Well, let's say another one is NH2 and an amine, AMINE. That's a different functional group. Well, that functional group will bend and stretch in a different way. So depending on the day, depending on what energy I give it, that workout routine is going to be different than the alcohol group. So the NH2 shows up in a different way in the spectrum. That's what we're leading to. So the infrared technology will allow me to determine functional groups on a molecule. I will be able to tell you if it is a ketone. Is it an aldehyde? Is it a carboxylic acid? Is it an amide? Is it an amine? Is it an halogen? Is there an alcohol? Is there an anhydride on it? We will go through a number of different functional groups to kind of determine what functional groups are present and how to look at the spectrum because of that. Now, before we go into the spectra, we need to talk about what samples are the best. Okay? Before I go in and start talking about spectrums and what these compounds are doing, you need to understand that a infrared spectrum can be taken of anything. A solid, a liquid, or a gas. It doesn't really matter, people. I have sample chambers that can take a gas vapor just like I can have a sample chamber that will take a solid. It's okay. So we can get an infrared of whatever compound that we want to get one from. It doesn't just have to be liquid. However, most of the time in the laboratory, we are looking at liquids. That's what we run most of the time. That's what we analyze most of the time. A lot of times in the organic world, most of these are liquids already. We will run across very few solids that we will need something from, but we have the technology in order to do it. So liquids are far and in between the most common sample that we do an infrared spectrum from. If I have a solid, a lot of times in the olden days, they would press that solid into what we call a pellet, and that's a KBr pellet. So we take the solid crystal, we basically make a disc out of it, and we put the disc into the machine and we analyze it. There's other ways to do that now. We don't have to worry about making disc and pressing disc in person, and it makes our job a little bit easier and a little bit quicker. So we'll talk about why these things are necessary a little bit later on when we start talking about pieces and parts of the instrument. Okay? So let's take a look at maybe some of the common functional groups that we might be seeing in the infrared world. And if you've not brushed up on your organic, well, I hate to tell you, this is truly organic chemistry here. So if you are new to organic, or if you're just now talking about functional groups in organic, well, you might as well learn them because we're going to be using them over and over in this course with this module. So up here at the top, you see the type of bond, a C triple bond N, and it gives me what we call a wave number. I'll talk about wave number in just a second. But it gives me a wave number. If it's present, this is where I would see it. And it gives me a description of what the peaks look like over here to the right-hand side. So for instance, if there's a carbon double bond carbon involved in the molecule, then I will see a positive signal in the area between 16 to 1680 wave numbers. And if I see a positive signal in that area, that could mean, not does mean, it could mean that a double bond is present in my molecule. So this is the table that we're going to have to start generating in our heads. And what I'm going to do, I'm going to break it down by functional group. So in each video that you will see upcoming, I will go through the functional groups and talk about the common shape and the area of the spectrum that you traditionally see them in. So that way we'll break it down into smaller segments. You can go through, figure out what you can pick up the easiest on, and then all the ones that you need refreshers on, you can go back and take a look at those and watch those couple of minutes and maybe get it the second time around that you watch it instead of the first time around. So we're going to be talking about these absorption bands and where these common molecules are going to be showing up. Uh, Something that we need to kind of keep clear is that we give you these ranges, or we will be giving you ranges of functional groups. And the ranges will always have a window. And the window is there for a reason, because we know that movement can happen, right? So for instance, when I make a general statement in the infrared region, that is a very general statement. That means most. Most of the time, this is where this will be located. Most of the time, if you have a double bond, this is where you'll see it. Most of the time, if you have an alcohol, this is where you see it. However, you need to keep in mind that these things can shift a little bit. There's some movement that can be associated with it, and it's okay if you see that happen. So these numbers that we're providing are averages. They can be a little bit above, they can be a little bit below, and that's all right. The reason that this happened is because of neighboring atoms. All right, so for instance, let's say that I have a carbon chain, and I'm going to take two carbon chains, and on one of them, I'm going to put an OH group here and a chlorine here. And then on the other one, I'm going to put an OH there and a chlorine one carbon down below. Well, in this case, the chlorine and the OH group are really close together, right? They've got a relationship with each other. In this example, the OH and the chlorine is a little further apart from each other. So they have a different type of relationship. And neighboring atoms, because of this, can give us ranges. That is why this is not ever one specific number. There are multiple numbers that are associated with these functional groups, and that's why we have to give you a window. That's why we can't give you just one number to go by, because all molecules are slightly different, right? And even if they all had OH groups and Cl groups that we analyzed, those molecules are going to show up slightly different than each other on the infrared. So it really is a fingerprint for the compound. Okay? So that's why you're seeing the ranges. I'll try my best to kind of give you one number whenever possible. However, for most of these, you're going to see a range of numbers that these positive signals can be measured.